Welcome back. This is part 2, Trig Functions, Year 2, Pure Maths. We're going to be looking at the identities and the graphs again for sec, cosec and cot briefly as a quick recap and a reminder. Then we're going to go through a few examples of solving trig equations that involve the reciprocal trig functions and then proving trig identities with sec, cosec and cot. So a quick reminder, we know that tan can be written in terms of sine and cos. As a result, we can generate a similar identity involving cot theta. It's the reciprocal of tan, therefore instead of sine over cos, cos over sine. We can also start with sine squared or cos squared equals 1, and by dividing through by either sine or cos, we can generate tan squared plus 1 equals sec squared, or 1 plus cot squared equals cosec squared. Okay, let's check the graphs. In every case, the graph of the reciprocal trig function can be constructed off the graph of the ordinary trig function. The scales on the y-axis of these are a little bit different, which is why they look a bit squashed in some cases, but you can see how the cosec graph corresponds to the sine graph in the sense that its lowest point is the sine graph's highest point in the first pi radians. The asymptotes on cosec correspond to the zeros on sine. The same thing happens with cos and sec, and then with tan and cot, they are essentially the same shape, but they are reflections of one another, and the asymptotes of one correspond to the zeros of the other one. It's worth practicing to see if you can comfortably and confidently sketch these graphs. I would always start by drawing a sine, cos or tan, maybe lightly in pencil, and then on top of that, on the same set of axes, you draw in the reciprocal. You can try a few key values on the calculator, but if you already have an idea of what the shape is, then you're off to a better start. Right, now we're going to look at some equations. I've chosen a few examples that I feel are slightly different to each other so that you can have a slightly clearer sense of which different techniques might be useful in different situations. To start with, the toolkit. You have your basic definitions. What I mean by that are things like cot is cos over sine. Tan can be written as sine over cos. Sec and cosec are 1 over cos and 1 over sine respectively. So if in doubt, you can turn everything into sines and coses and then work with it from there. In fact, the identities that we've generated, they came from those basic definitions. So although the identities are often very helpful and can save you a bit of time, they're not essential. You can, with a bit more work, turn things into sines and coses and use the standard sine squared or cos squared equals 1 identity to break apart equations or identities. But you'll find the identities are very handy. And just as a quick demonstration, it doesn't take a very long time to recreate them. I never recall these. If I think about them, I can remember which one is what and where the things are, but it's not the sort of thing that you would need to necessarily memorize, because you already know sine squared or cos squared equals 1. That comes from Pythagoras, so if you need a reminder of that one, you can sketch yourself a picture of the unit circle, and you've got your sine and your cos as your opposite and adjacent sides. The rest come from either dividing through by sine squared or dividing through by cos squared, depending on what you want. So I'd say it's a good thing to sketch in the top right of your page as soon as you do a trig question, because then they're there for you as soon as you need them. Not only there, but you won't necessarily recognize when you've got something that links to one of those, especially when you're first starting out, unless it's already written on the page for you. Okay. One other thing. If you get to the end of a trig question and you find yourself looking at sec x equals 2 or cot x equals minus a half, and you're trying to do that final step that you would naturally do with cos or with sine, you'll struggle because there isn't a sec to the minus 1 or inverse sec button on the calculator. Luckily you don't need one. Think back to where sec came from. It's the reciprocal of cos. So although I've written this in 3 steps, you would normally do it in just 1 step. Take the reciprocal of sec x and you turn it into cos x. The reciprocal of 2 becomes a half. Alright, let's start by looking at the first question. 3 sec squared x equals 4. The first thing I would do, as in any other example where you've got a trig equation to solve, is try to turn it into an equation that involves just a single trig function. This one already does involve a single trig function. and then try to turn it into a linear equation involving a single trig function. This one's quadratic, but we can solve quadratics, especially quadratics that look like this. It's just a case of rearrangement. So if sec squared theta is 4/3, you could go about this two different ways at this point. You could square root and have sec theta equals the square root of 4/3 or the negative square root of 4/3, or you could do the reciprocal straight away. We're going to need to at some point anyway, and this saves me thinking too hard later on in the process, perhaps. It's up to you. Comes out the same either way. But if cos squared is 3/4, then you have two different results. Either cos theta is √3/2 or it's negative √3/2. Don't forget both results. They're both important. You're going to need both of them. Otherwise, you'll have missing solutions at the end. At this point, you generate solutions within the range. We had a range of 0 to 2 pi. So our solutions are pi/6 and 11 pi/6. Where we get those from? Well, the first one comes from the calculator. That's called the principal value. And the second one will come from the symmetries of the graph. If we have a quick look at the graph, if we draw on a line representing y equals √3/2, which is about 0.87, we'll see that there are going to be two solutions, and one's quite close to 0, and one's quite close to 2 pi. That corresponds to the pi/6 that we found from the calculator, and then further along, we end up with the 11 pi/6, in other words, the almost 2 pi value down here somewhere. So those are our two values, and they seem to fit, they make sense. And when we get to -3 pi/2, you'll have a similar line. You could even do it on the same graph if you're feeling lazy. And we're expecting values that should be, well, still symmetrical, but they should be closer to the middle. So either side of pi. Mine's not the most accurate. My line should probably be a little bit further down, but that's the whole point of this. It's a rough sketch designed to help you to identify the symmetries of the curve. However, you might prefer using the unit circle method. I really like this one. It's something that I've only recently come back around to, if you like. It's not the same as the cast diagram that some of you have used. I'm not such a fan of that one because it doesn't give me the reason why behind something. So it's an easy one to get mixed up with if you're not completely confident with it. And I've seen a lot of year 13 students get confused with the cast diagram and become over-reliant on it and then struggle when it doesn't quite work. The unit circle method essentially says cos relates to the x-axis. So whenever you're dealing with cos, you're looking at the horizontal displacement. This is also helpful because it ties in with mechanics. When you resolve through an angle, you're looking at cos, and when you resolve away from an angle, you're looking at sine. So in this case, the angle that we're dealing with, if I can do a theta, there we go. The angle you're dealing with will be the angle which gives you this specific displacement. If we look for our 0.866 value on the x-axis, we'll find there are two distinct places on the circle where that occurs. It happens up there and it happens down here. Those two places correspond to our two solutions. One of them is just 30 degrees up, and that one we get from the calculator. It's the other one we get by symmetry. We say, well, you can think of this one in two different ways. You can think of it as minus pi/6, which is perfectly valid, or you can think of it as going anti-clockwise all the way around the circle, almost a full 2 pi radians. In other words, 2 pi minus pi/6. Now, I quite like this method. It seems to work quite well. And of course, you can see again on the same diagram, if we have -3 pi/2, not only can we see how those two solutions link, 5 pi/6 and 7 pi/6, but we can see how they link to positive 3 pi/2 as well, which is somewhat less obvious when you look at the graph up here. We can see it more easily from the unit circle. So if that's something that you'd like to try, then by all means give it a go. And if it's confusing you, post something on the forums, because there are people in the class who use the unit circle and find it works really well for them. This next question involves cot squared theta and a tan theta. So the first thing I thought of as soon as I saw this was that perhaps it's a disguised quadratic. With a bit of messing around, maybe we can make it so it's a quadratic in tan theta, for instance. But if you have a quick glance across at the trig identities, which you will have helpfully scribbled down in the top right of your page, we see that cot squared theta links with cosec squared theta. In other words, we could turn cot squared in this equation into a cosec squared, or something involving cosec squared, but we couldn't turn it into a tan squared. Tan squared links with sec squared. So although this may on the surface look like it involves identities, in this case it doesn't particularly. Instead, we're going to have to resort to the more fundamental basic definitions version. So let's try that. Let's break it apart into its component pieces and see where we get to. I should mention this is not the only way to do this. It's possible in this case, certainly, to rewrite cot squared as 1 over tan squared, and then the entire thing turns very quickly into a cubic involving tan. But I wanted to show you how I did it when I first approached this question, because it's likely that this is the kind of thing you will do with a lot of the more complicated looking questions. You don't necessarily want the most efficient route through. You want to see how pretty much any sensible route should help you to get closer to the answer. So I turned it into cos squared over sine squared minus 8 lots of sine over cos. And then we do some sensible things. So sensible things in this case involve either rearranging so that we've got the 8 sine over cos on the right hand side of the equation, or perhaps you would choose to multiply through by the sine squared and the cos theta to deal with those fractions. Once you've got rid of the fractions, you've got a slightly nicer equation to deal with. I've done both of those things, and now I have cos cubed equals 8 lots of sine cubed. You could cube root both sides at this point if you like, but you might find it easier if you notice that because it's cos cubed and sine cubed, you can divide through by cos cubed and out comes tan cubed x. You could divide through by sine cubed, but then you'd get a cot cubed and you'd still have to take the reciprocal afterwards. As soon as you've got it down to a single trig function, we can sort it out. We get tan theta equals a half, because that's the cube root of an eighth. Notice that it's not plus or minus a half, because if you do minus a half cubed, you get minus an eighth. So there is only one cube root of an eighth, at least until we get to complex numbers. So we generate two numbers here. The number's not particularly nice, but we get 0.464 from the calculator, and we get 3.605 just by adding pi. The nice thing about tan is you don't really need a graph. You don't need a unit circle. All you need is to remember that every single value is going to be pi above another valid value and pi below another valid value. Once you've got a solution from the calculator, add as many pi's or take away as many pi's as you like to generate more solutions within your range. If you want to see it on a graph, it looks something like this. Every single branch is the same. So if you've got a solution on one branch and you want to jump to the next one, you just need to use the period of the graph. Remember, you can test your solutions. You can check back at the very beginning. You can sub your numbers in and check that they really solve it. You just need to be a little bit careful, because cot squared theta is not something you can type into your calculator directly. You need to think of it as 1 over tan squared theta, or in some cases you need to think of it as cos squared over sine squared. So you end up moving down the chain a little bit. And if you've made a mistake somewhere along the way, you might just prove that your solutions satisfy line 2 of your equation, perhaps, rather than the original equation. For our third example, this one is something which matches the trig identities. If we take a quick look at the top of our page, we notice that cot squared theta and cosec squared theta play very nicely together. And remember, just because cosec squared looks like a more important term because it's been squared, it doesn't mean we're going to turn this equation into something involving cosec. Because cosec squared is the bit that can most easily be converted, we convert the cosec squared into, in this case, 1 plus cot squared. So that's the first step. And although I've included brackets here, obviously it's not essential in this particular case. I would, however, encourage you to do this in general, because the more you get into the habit of every time you replace a single term with a term which is built from multiple separate terms, added or subtracted, if you always put it in brackets, then when there's a 2 in front, or when there's a squared after it, or when there's a negative, you will automatically have the brackets there that you absolutely need. Otherwise you'll end up messing things up. I've done it myself. I did it this afternoon, so it still happens. You need to be aware of it, and in as many cases as you can, try to mitigate the issue by planning for it ahead of time. When we simplify this and rearrange it, we can see more obviously that it is just a disguised quadratic. This one's a quadratic in cot squared. You could divide through by cot squared theta, or equivalently multiply through by tan squared theta to turn it into a quadratic in tan theta. However, it's probably just as easy to deal with it in terms of cot squared theta, probably slightly easier to factorize, to be honest. And we can turn our cot theta equals equations into a tan theta equals equation at the end in much the same way that has been demonstrated. If you remember down here, if you have sec equals something, you can make cos equals something shortly afterwards. So this factorizes. If you choose to use a substitution, make sure you're clear and explicit. Quite a few people were very good at that in the questions that I was looking at recently. If you decide to replace cot theta with a c, don't get confused later on and think it's a cos theta or a cosec theta. State clearly what you're using and then make sure you remember what it was afterwards. The best way to remember it is to state it when you first introduce it. But ideally, avoid that necessity by practicing factorizing things in the form that they're in. Then you don't need to worry about any kind of substitution. Now we've got two solutions here, and one of them, if this had been a cos theta, we would immediately reject. But remember, because sec, cosec and cot are different to sine, cos and tan, they have a different range and they will potentially have different values that you would reject or accept. For cot theta, any value is fine. It's just like tan. You can do inverse tan of anything, you can do inverse cot of anything. If this had been sec or cosec, the problem values would occur when you get a fraction, like a half or minus 3/4, and it would not be a problem if you had a value that was larger in size than 1, or, as in this case, equal to 1. So it's worth being aware of that. The things that would normally break a sine or a cos do not break a sec or a cosec, and vice versa. So, we convert these by taking the reciprocal of both sides. Take care to actually take the reciprocal. It's tempting because the one on the right stays the same to keep the one on the left the same, but watch out and make sure you're getting sensible values for that. If cot theta is 2, then tan theta is the reciprocal of 2. We can find our values for tan theta equals a half, just like on the previous example, and we can find our solutions for tan theta equals 1. We can get exact solutions for that one because tan theta equals 1 corresponds to that classic right-angled isosceles triangle with 45 degree, 45 degree, 90 degree. It's one of the two set squares that you might be provided with in a math set, which these days people never use. But if you have a pi by 4 angle in your triangle, then the opposite and adjacent sides are both equal to 1, or both equal to whatever they're the same as. And if you do sine or cos of 45, you'll get 1 over root 2. If you do tan of 45, you get 1. Now we move on to proving identities. These are fundamentally different to equations. You'll see on this slide I've used the triple equals sign. I won't always remember to do that, and it's not necessarily a cardinal sin to forget it, but it's useful to be aware of and to point out at the beginning, because what we're dealing with here is not an equation that we're trying to find solutions for, but this is a statement that two things which on the surface may look different are underneath exactly the same. Sec squared theta plus cosec squared theta, according to this claim, is identical to sec squared theta multiplied by cosec squared theta, regardless of the value of theta. Somehow the sum of these two functions and the product of these two functions should always be the same, and it is not obvious immediately why that's the case. It's our job to prove that that's the case, and one important thing you need to be aware of here is that you cannot just start with that as if it's an equation and then start messing around with both sides. If you do that, essentially what you're doing is assuming to be true the thing that you've been asked to prove, and then going on to do things based on that potentially faulty assumption. Whether or not that assumption is true is irrelevant to what you go on to do with it. Again, our toolkit includes the basic definitions of all of these trig functions. In other words, we can write them all in terms of just sine and cos. The identities, if we can see an identity to use, it's often a quicker thing to work with than turning everything into sines and coses. And then there's a third thing which becomes a big aspect of proving identities. There's usually some kind of trick. Now, it's not an endless supply of tricks here, but anything algebraic that you've discovered, difference of two squares, or sometimes things like rationalizing denominators. It's not exactly that, but you'll see examples where multiplying the top and bottom of a fraction by something clever so that you get 1 minus sine squared theta comes in really handy. You'll find a few tricks like that appear as you work through these, and that's why trig identities are a particular area of maths that you'll probably hate quite a lot to begin with, and then learn to love as you go along. We start with the left-hand side. We work exclusively with one side of this identity, and the aim is to, through logical manipulations, to demonstrate that it is in fact identical to the right-hand side, regardless of the value that theta takes. Now, I've just used the basic definitions because it's not clear to me exactly how these two things are going to end up being shown to be the same. But as soon as you use the basic definitions, we now have something which we can work with. We can do algebra to it, in the sense that we can clearly see there are things we can do to write this in a fundamentally different form. It's two separate fractions. We can add fractions together, and that's a logical choice to make, so we do it. If we add the fractions, you'll find that the left-hand side fraction becomes sine squared over sine squared cos squared, and the right fraction becomes cos squared over sine squared cos squared. Put it all together, and hopefully you notice sine squared and cos squared appears on the top, and we know that that's equal to 1. At this point, you should be rubbing your hands in glee, because you can already see, if you're comparing at every stage, you're looking at what you're trying to prove, and you're wondering how it might be the same, then when you get to something which is more and more similar, you can start deliberately manipulating it in order to make it do what you want it to do. So at the end, we break it apart, make every step clear and explicit. The watchword here is be convinced. When the examiner is looking at your work, they will be referring to a mark scheme which urges them to be convinced that you know what you're doing. It's not enough to skip a couple of steps just because you know what to do. You need to demonstrate that to the examiner by making sure everything you do is explicit. You can state why you're doing what you're doing. It's not necessary here, for instance, to write down sine squared over cos squared equals 1, therefore. That's a bit overkill. But as long as this is clearly written in this form, and when that's the only thing that changes, it's clear to the examiner how you know that that's what's going on. When we get to the end here, we write it in a way that it's obvious that we can then turn it into the thing we're looking for. And at the end, you'll notice now we have an unbroken line between the left-hand side that we started with, and the right-hand side only appears when we have actually managed to create it. The left-hand side is this, which is this, which is this, which is this, which, oh, would you look at that, turns into the thing we were trying to make it to be at the beginning. We never assumed it was. We demonstrated that through a series of logical steps we could create it. Remember that if you start with both sides at the same time and start messing around, you're essentially constructing a circular argument. You're saying, well, if that thing is true, then such and such, then such and such, and maybe you go on to prove that 5 equals 5 and you think that you're very clever. But just because what you've started with does not automatically result in a contradiction does not mean that it's valid. The absence of evidence is not evidence of absence, as they say. If you can start with an assumption and go on to prove that it is by its very nature fundamentally contradictory, then you can prove it to be false. But just failing to prove that it is by its nature fundamentally contradictory does not demonstrate that it is definitely true. I'm going to this next example I've chosen because both sides of the identity look complicated. Often there is a tricky looking side to an identity and a simpler looking side. And it makes sense to start at the more complicated looking side because there are naturally things you can do to simplify a complicated expression and turn it into, hopefully, the simple expression that you're aiming towards. It's not usually very easy to go the other way. It feels like an uphill battle. Now what we're looking at here is, in my head at least, two complicated expressions, and I can't easily see a way to simplify one and turn it into the other one. But it's possible that by simplifying the left-hand side and at the same time simplifying the right-hand side, we may end up finding common ground in the middle, proving that both simplify to the same thing. Think of it as comparing two fractions. If I ask you to determine whether, let's say, 6/24 and 9/36 are the same, it will be a little bit awkward to do a direct comparison because 6 doesn't easily turn into 9 without multiplying by something horrible like 1.5. But if you simplify 6/24 and you also simplify 9/36 and you compare their simplest forms, each one is 1/4, therefore the two must have been the same. That's what we're going to try here. We still start the same way. So you don't even need to know that you're going to try from both sides when you begin. You might get lucky and find a way of barreling through from the left-hand side to the right-hand side all in one go. But to begin with, you pick a side and you do sensible things. I'm rewriting things in terms of sine and cos, and then because I have two separate terms, I'm going to think of them as two separate fractions, and I'm going to add them together, or in this case, subtract. To give myself a common denominator, I've had to change sine squared x into sine to the 4x over sine squared x. So now I have 1 minus sine to the 4x over sine squared x. I don't know about you, but I can't immediately see that as looking like cot squared x plus cos squared x. So I draw a line down the middle of my page, and I start out on the right hand side. I do similar things. I turn every term that isn't immediately sines and coses into sines and coses. I've got something similar-ish to what I had on the left. In fact, I've got a fraction and an additional term. I can combine them to make them into a single term. In this case, cos squared x needs to become cos squared x sine squared x over sine squared x, and then I can add the two together. Now, if there are any other logical things to do at this point, then I do them. You don't have to hunt too hard. Usually something will jump out at you if you're writing it sensibly. Cos squared x is a factor of both terms of the numerator. So it is a factor of the entire numerator, and I can factor it out like that. At this point, you want to make sure you're keeping an eye on what's going on the other side. You're looking at both sides, much like when you're trying to find the lowest common multiple of two numbers. You want the lowest common multiple of 17 and 20? Well, you might start by writing down a bunch of multiples of 20, and they're easy, so you might go a long way, but after a while you're going to need to stop and ask yourself, well, do I have a multiple of 17 yet? So you go back and forth between the multiples of 17 and the multiples of 20. You list multiples of 17 until you get bored, and then you go back to the 20s, and at each point you're always keeping an eye on the multiples you've already done, so you don't get too ahead of yourself with one column compared to the other one. It's similar here. You need to be looking at what's similar and what's different. We've now got the same denominator on both sides, which is very promising, because I'm trying to prove these two things are the same, remember? Well, if the denominators are now the same, and both of them are written as single fractions, it should mean that there is a way of linking the numerators. Can we prove that the numerators are the same? So focus on these and see if there's anything that jumps out. Well, we have a 1 plus sine squared here. We have a cos squared here. But over here we've got 1 minus sine to the 4. Well, if these are the same, then 1 minus sine to the 4x should factorize to give cos squared x times 1 plus sine squared x. It doesn't have any coses in it, but it does have sines. Maybe you've spotted it by now. On the left-hand side, we can use the difference of two squares. And hopefully, even if you hadn't seen it initially, and some of you will have done, and well done if you did, even if you didn't see it initially, hopefully by the time you get to the point when you see a 1 plus sine squared x appear here, it makes you think, maybe I can get that term over on the left. And as soon as you do that, it all sorts itself out. 1 minus sine squared x is automatically going to turn to cos squared x. So at that point you can just carry on from wherever you happen to be. 1 minus sine squared x is cos squared x, and now if you notice, we've got two things which are the same. They may not look much simpler in the end, but they were natural simplifying steps, so they are downhill, if you like, from both sides. And once you find two things that are the same, there's a very simple way to finish your proof. You can say, well, this thing is identical to, let's give it a name, capital P. It doesn't matter what P is, what matters is both of those things are equal to P. And if the left-hand side is identical to P and the right-hand side is identical to P, we can say, therefore, the left-hand side is identical to the right-hand side. And my proof is done.